Welcome to another session of Basic Mathematical Analysis class. Today we will discuss about the complex function as mappings. So in order to study a map is to study about the graph of the function. But in this case, when you are dealing with the complex numbers, it is very difficult to draw the graph since our graph is lying in the four-dimensional space. So we will have an alternate as complex mapping. So the concept of complex mapping provides an alternative way of giving the geometric representation of a complex number. Now we will use the term complex mapping to refer to the correspondence complex mapping to refer the correspondence determined by the complex function w equal to f of z. So we will refer w is equal to f of z as complex mapping between the points in the z plane and images in the w plane. Now we will have two planes here. First one, we will say that this is going to be the z plane because here we are having a curve over here. Okay, this is our z plane. So we will represent z equal to x plus iy. So this is going to be our real axis. Then let me mark it as x, and this going to be a imaginary axis, that is y. Now we will map this to some f of z, that is w. So we will have another plane which is called a w plane, and we will have the image of this here. So somewhere here we will get the image, and we have mentioned w we will always represent with u plus iv. So this is going to be your u axis and this is your v axis. So this is the general method that we are using. In some cases we can have this w plane over this z plane also, or we can have side by side these two planes. So this is the first thing we want to mention here. So in order to create a geometric representation of a complex mapping, we begin with two copies of complex plane, the z plane and the w plane, drawn either side by side or one above the other. The complex mapping is represented by drawing a set S of points in the z plane and the corresponding set of images of the points in S under F, and this we will represent as S dash. So we will map F of S as S dash. That's the next thing, notation. So image of S under F, that we are mentioning as S dash. So in the same way, if when you are taking C as a curve, we will represent f of c, the curve as such, as f c dash, and if D is a domain, then we will have the image of this domain we will represent as D dash. This is the usual convention that we are using when you are dealing with complex maps. So here is given one figure. S is going to be our z, and you are finding what is your f of z, and f of z you are getting another one. See here we have represented this axis as x and y because z equal to x plus y, x plus iy. Then here we are having u and v. So here you are representing your f of z, that is nothing but w, as u plus iv type. Now let us examine what is the image of some maps. So here is given first example as w equal to iz. W equal to iz. So the map is when you are having z equal to x plus iy, then your w is nothing but iz, that is equal to I into x plus iy. So this will reduce us as xi minus y, right? Now let us examine what will happen under this map. The half plane, that is real part of z, is greater than or equal to 2. So real part of z greater than or equal to 2 means x is greater than or equal to 2. That means you are getting a vertical line over x equal to 2, and this shaded portion will be your required plane. Now we want to find the image of this blue shaped region under the map IZ. Now first of all, what you are going to do is we will consider this vertical boundary, that is this line x equal to 2 line. Now consider first the vertical boundary line x equal to 2 of s. Now for any point z on this line, what will happen? If any z on this line can be taken as z equal to 2 plus iy, where y can vary over the entire real number. Right? Now we want to find what's the value of f of z. So f of z equal to iz. So that will become I into 2 plus iy. Now this reduces as 2i minus y. So when you're having this ux plus uxy plus I into vxy type, it will reduce as uxy as minus y and vxy as 2i, right? That means 2. So this is going to be a new function. So in this line, see, we have find out what is w. W is f of 2 plus iy, that is this thing you are getting exactly the same. Now the set w is equal to is the line v equal to 2 in the w plane. See, v equal to 2, y can be anything. So v equal to 2 means we will have this one as like this. See, v equal to 2. This dark black line, this black line represent that image of the line represented as in blue here. Now we conclude that the vertical line x equal to 2 in the z plane is mapped onto the horizontal line v equal to 2 in the w plane by the mapping w is equal to iz. Therefore, the vertical line shown in color is mapped onto horizontal line. Okay, and now consider the entire half plane as shown in color. That is, now we have finding what is the image of an arbitrary point over here, here, and here. So what will be that images? So in general, we can say that any point lying in that region, that is x equal to 2. That means this region, any point if you are taking, its x value should be greater than or equal to 2, and y can be varying over the entire real number. Now in order to describe the image of S, we express the mapping w is equal to iz in terms of its real and imaginary parts u and v. So as we have mentioned, we will get the equation uxy is equal to minus y and vxy is equal to x. Call this as equation 2. Now you can combine this equation 1 and 2. So what we will get? So by combining these two, you will get x value, that is v. V is greater than or equal to 2. See, when you are comparing, you will get v is greater than or equal to 2. And next one, we are having y value is varying over minus infinity to infinity. So here your u value will vary over minus infinity to infinity. That is the set S dash, that is the image of S under w is equal to iz, consists of all points w equal to u plus iv with the condition u is varying over minus infinity to infinity and v is greater than or equal to 2, and we can plot that too. So when you are plotting that, you will get exactly this one, that is your v value should be greater than 2. That means this is the value v equal to 2. This line v equal to 2. So what if the point coming above this line will represent our s dash. So your s dash is this. So this is the first example. Second example is image of the line under w equal to z square. So we can proceed in the same manner. So here the map is we want to find the image of vertical line x equal to 1 under the complex mapping w equal to z square. So x equal to 1. What this line? If you are representing as this is your x and this is your y, this is a z plane. Okay, so this z plane you want to represent x equal to 1. So x equal to 1 means, suppose this is point 1, a line passing through this point, right? This is the point 1. Now this is the line x equal to 1. Now we want to find its image in the w plane, right? So x equal to 1 means we can have the z as 1 plus iy, where this y can be any real number. So we can have minus infinity, less than y, less than infinity. So this is our required z. Now we want to find what is your f of z. Now how to find f of z? By definition it is given as z square. So f of z equal to 1 plus iy whole square we will get, right? So when you are squaring, you will get this as 1 minus y square plus I into 2y. Now representing this as u and v, you can have this equal to uxy plus I into vxy, with the condition that uxy equal to 1 minus y square and vxy equal to 2y. Nice. See, u is equal to 1 minus y square and v equal to 2y. That we have got, where your y is ranging over minus infinity to infinity. Now this equation 3 and 4, we can say that this is the parametric equation in real parameter y, because both are depending on this y value, and they define a curve in the w plane. Now we want to find which curve it will represent. So we can find the Cartesian equation in u and v for this curve by eliminating the parameter y. So we can have these two equations. First equation is u equal to 1 minus y square and v equal to 2y. Now from this you can have the y value as y equal to v by 2, right? So you can substitute this, we'll test this 2 and this 1. Now substituting 2 in equation 1, what we will get? We will get your value as u equal to 1 minus v by 2, right? Or square. So when you are squaring, we will get, that is u minus 1 equal to minus, am I right, v square by 4 you will get. So when you are having cross multiplication, you will get v square equal to 4 into u minus 1. What is this one? V square equal to 4 into u minus 1. You can compare this with your equation y square equal to 4ax, right? So it will represent a parabola. Okay, instead of x we are having x minus 1 type. So that means the center is, what's the center now? Center is You studied this, right? When you are having a parabola of this type, your center and what should be, we'll say that the lattice rectum, right? Lattice rectum we will say. So what is this points? So the vertex should be 1 0. For this parabola, vertex should be, for this it is 0 0. But comparing this with this, we will get this parabola is of vertex 1 0 and u-intercept is 0 plus or minus 2. So we can represent this parabola in this fashion. See 1 0 and it's, see 1 0 is the vertex you are getting and this is going to be 2a we will say. So here a equal to 1 you are getting. So not a equal to, not 1, 1 by 2 you are getting. So it is u-intercept is 0 comma plus or minus 2. So in general we can say that this is mapping, this vertical line is mapped to a parabola like this. So this is the how we are finding the images of a complex map. Okay, let me conclude this session here. Let us continue in the next session with parametric equations of a curve and how you are finding the parametric images of a parametric curve. Okay, thank you.